Thank you again. All right, let's move on. So we were saying that um, we are in Kingston, and we need to know how long it would take us to go from Kingston to Trelawney. This is Falmouth right here, right? And the distance, for example, it's not actually 3 kilometers, right? But let's just say it's 3 kilometers for argument's sake, and we convert this to 3,000 meters. We have to convert from kilometers to meters. Um, so yeah, so we say this is our formula, and we want time. We have the distance and we have the velocity. Now we need the time. So the time we have to transpose, have to multiply both sides by t, and we get this, and then eventually we have to divide both sides by v. So we put v down here, these cancel, and we're left with t equal s over v. And we use this formula here. That's what we're going to use now to calculate the time. Right? Are we good so far? You can type in the chat, yes sir, no sir, or you can use a mic.
Yes, sir.
All right. Mr. All right, Mr. DeMarco says no. All right. So let Mr. DeMarco please tell me where you're not really getting no.
Convert what? Wait, sorry, I convert 3 meters.
3 kilometers. So this is 3 kilometers.
Oh, 3,000 meters.
Yeah. So 3 kilometers,
Can you turn that down, please?
right? Um, 3 kilometers, and we're converting that to meters, right? So you have a better understanding now, or you want me to go through it, the conversion?
There go 3 conversions.
All right. So I'm going to need a help, right? So 1,000 kilometers, 1,000 meters is equal to 1 kilometer, right? Is that so?
Yes, sir.
Right. So we have 3 kilometers. So we place this over the 3 kilometer side, 3 kilometers, and we want to know this right here. This is our question, or this is our x, right? We want to know
Oh,
this over here.
multiply.
We cross multiply, right?
Yeah.
Cross multiply. So we cross multiply, cross multiply. So we're left now with um. Sorry, this looks a little jumbled, right? Just bear with me, right? So we cross multiply, and we now get 3,000 kilometers, right? 3 times 1,000.
Yeah, man, I get you.
3,000 kilometers, right?
Yes, sir.
Equal, and we cross multiply equal x. So x is now 3,000 meters, right? Understand now?
Yes, sir.
All right, good. Now we plug in. So what goes up here? T equal, what goes at the top?
Three, three, 3,000 meters.
3,000. And what goes down here?
Three kilometers, sir.
Remember we
Oh,
have
80,
80 meters
80,
per
sir.
second. Right. So
80.
somebody want to calculate that for me, please?
37.5.
37.5 seconds. That's not true. What let's just say. Right?
No, that wrong.
Sir,
That's
repeat
totally
yourself.
wrong.
It should be correct. But I'm saying it's not possible in real life. That's what I'm trying to say. Alright? Divided by 80. Oh no. No, that's wrong. Wait. 3,000. Somebody do it for me, please. 3,000 divided by 80 again. Oh yes, 37.5. Right, it's correct. All right, but it's not possible in real life. We'll leave acceleration for another time. I want to touch on linear momentum quickly, right? How much time? We have 15 minutes left. So let's just touch on linear momentum. Next class, we will do back acceleration. All right.
Alright. Let me tell you if it was on the device, don't make me remember. Alright.
I'm going to mute some mics. Please excuse me. All right. All right. Hush, hush, little baby. All right. All right. So, as I said, we have a person coming in. We'll move on now to Newton's three laws of motion. We want to get to that first before we actually come back to acceleration, right? Because we need to have an idea of Newton's three laws of motion. So, in Newton's three laws of motion, right? An object, just ignore this, right? Another arrow. So an object will rest. An object at rest will stay at rest, and an object in motion will stay in motion with a uniform velocity. We see this word coming back to haunt us again. Uniform velocity. Unless an external resultant force acts on it. Right? Unless an external resultant force acts on it. Anyone ever seen this before or heard about this before? Newton's three laws?
When two objects collide, sir. Two
No,
moving
not that
objects
one.
collide.
Not
Oh.
that one. Newton's first laws. The first one. Right? So the first one says that an object at rest. So if an object is at rest, it will stay at rest, right? Unless we move it. So if there's an object here, unless we push that object, it will not move. And an object in motion will stay in motion, right? With a uniform velocity unless an external horizontal force acts on it. So what would this external horizontal force be? Somebody want to give it a try?
Like your hand or something. You push it.
It is in motion. Let's just say a car is driving. Right, we have a car here that's driving, right?
Yes,
And
sir.
it will eventually slow down, right?
Yes, sir.
Why?
There.
Because lose momentum.
Yes, mate, done.
Not really, not gas and
Take
momentum.
I guess.
Friction. Newton's.
What
If
about
lose momentum,
friction?
sir. Oh, friction.
Yeah. So when you're traveling on the road, remember that friction would cause if friction could create a pullback force. So we're going in this direction. We're going this direction, but then friction will cause us to pull back, and slowly and eventually we will stop. So this leads us now to the definition. We'll go back over this again next class, right? But this leads us now to inertia, right? Inertia of an object is the resistance of an object to change its position, right? So an object which is at rest, as we spoke about, let's just say this object is at rest, right? It will do everything in its power, right? I am here and I'm pushing it. I am pushing the object, right? It will do everything in its power to stop me from pushing it. So that's resistance. So just remember this word, inertia, right?
Yes,
You will see this word popping up. Please tell me if I'm moving too fast or you want me to repeat it over again.
Repeat it, sir.
Right.
There, I still cannot find it in the book, sir.
Yes.
You
Distance
still
and
can't find
displacement.
it.
Yeah.
All right, no problem. I will look on it afterwards. All right.
Oh, yes, sir.
Go ahead.
We can enter Google Classroom.
You can't enter it.
Yes, sir. I can't.
All right. I'll deal with that after the class. Right?
All right, sir.
Yeah, just bear with me for a second. I will deal with all the queries after the class. All right. So
All right, sir.
for Newton's first law, let's just repeat it. An object at rest will stay at rest. So if we leave an object, if we leave an object, it was before the object, before we start pushing, if we leave an object here, right, the object will never move unless we begin to push it. So an object will stay at rest and an object will stay in motion. So if a car is driving, right? If it's at a certain velocity, if there was no friction on the road, right? Say it was on a slippery slope, or let's just say it was on a very slippery
Okay.
surface, right? No
Mm.
friction. That's what the road is for. The road is used to produce friction, right? To control the speeds of the car, right? So
Yes, sir.
if we're on a slippery slope, right? Remember, you're not supposed to drive fast on a slippery when the road is wet because it's very slippery, right? So if we're on this slippery road and we're moving at a constant velocity, unless we have to have a stronger resultant force to stop the moving car. What
Okay.
would that be? What for example, what would that be? That would be
Or
the brakes,
wheel,
right?
more grip on the wheel.
Right, and more grip on the wheel. So these are things that we put in place to cause us to control the speed of the car, because if it weren't for friction, then we would eventually crash all the time. Right? So these are some things that resultant force. For example, as I said, we move something, it will never move until we start actually moving it. And then this right here, this definition, inertia, right, of an object is the resistance of the object to change its position. Right? You won't need to necessarily memorize this. You just need to know about it, know inertia. That it's just the opposition that we put up. Right? We good so far?
Yes, sir.
All right, good. All right, so we move on to Newton's second law now. This is where things get interesting, and we'll pause on the second law for a while to deal with momentum. The momentum is a lab that you will do. So all of these are just some basic things leading up to momentum, right? We need to touch on this today. We have to at least get an understanding on it today.
Then
I see a
I
message in the chat.
if it make move as come out,
Sure,
sir.
you can go ahead, but we can't stop because we have 9 minutes. But you can
Yeah.
have 8 minutes to complete the class, so you can go
A
ahead.
question. Okay, a question.
Go ahead for gas school, go do your labs then.
I hear a question.
Huh?
I hear a question.
Oh, sir, may I ask you if I not get the go ahead to
No, no, we haven't gotten the go ahead to come in and complete labs. We really need to do it as soon as possible.
Nice.
Mr. Evans, you're serious thing with the fan
yes, sir,
joking.
because I go
It's
over school
really, it's really
and
out of our hands. You're saying something?
Sir,
go
element
over
is
school
important.
Friday. And it's a no student.
Yeah. So, Israel the government is instructing us not to keep students on campus because they don't want any problems. All right.
Sir, I know we go off looking at them.
I, uh, let's we're trying to make the best of the situation. Right? It's going to affect both of us. Everybody's affected, right? But we just have to just make the best of it, right?
Sir,
All
that
right,
was
let's
a
move
mistake.
on.
Yo, up in the
So Newton's second law, right? We have 7 minutes. Let's see how much you can complete. So force is directly proportional to mass times acceleration. Anybody remember this? We spoke about this. Remember this word here, directly proportional, this phrase.
Since
So as force increase, this would decrease or increase. Which one? Mass times
What, sir?
must increase.
Increase, sir.
would increase. Why? Because they are
Directly proportional.
right. So it's the same thing over here. They're in the same line. So force equal mass times acceleration. Remember mass here and we have acceleration here. As I said, next class we'll go over back acceleration. But as this increases, this will also increase. I just want to introduce you to it, right? So 1 Newton, which is the unit for force, force is in newtons, right? 1 Newton is the amount of force that is required to move 1 kilogram. Remember, mass is in kilograms. mass is in kilograms, of an object with an acceleration of 1 meter per second, right? And we will dive deeper into this as we move further down. But if you have any questions, you can go ahead, right? You have 5 minutes. All right, no questions. So this is important now. Um, Linear momentum. So we'll go over this again, right? Next class. So
Yeah,
linear
but the
momentum.
ability if the Lamborghini slower than the buggy, you know, sir.
Right? We get in there, right? So linear momentum is the term in physics that is used to describe an object with a mass m in motion, right? So it's nothing too technical. It's nothing to worry about. We just use it. So if we have a larger mass and a larger velocity, we will have a higher momentum or a larger momentum. Now the symbol for momentum, we will disclose a future down, right? The symbol looks like this. But as I said, don't stress yourself about it, right? There's nothing to worry about. What you need to worry about now is the formula. So remember that momentum is considered a vector quantity, right? A vector quantity. Why? Because of this guy right here.
Velocity.
Right, because you see with the vector and the vector quantity is coming up back again, velocity coming up back again. We
Yes, sir.
covered a lot today, right? We covered a lot. All right. Now, let me just ask this quick question before we go. Right, this will take us about 4 minutes to discuss. So this car, right? With
Sir, on BMW i8, sir.
Yeah, somebody slap you.
On
That's a
BMW.
Lambo there. That's a Lambo. Lamborghini.
this
Oh,
Corolla,
clone this dog.
Aventador.
this Corolla,
Boy, say
right?
I hate.
This is our Corolla. Corolla, no?
Corona.
All right,
i8, sir.
Aggressive.
all right. So
On i8.
this is our Lamborghini, right? And it weighs 1,000
Fine.
1,000 kilogram, right?
Yeah.
And this has a velocity of 25 meters per second. That's how fast it can go. While this fast car over here, right, weighs 1,500 kilogram, right? It's very fast, very 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 fast. And this is the fastest that this can go, 35 meters per second, right? We should have the higher momentum.
Very Lambo,
You
sir.
know the
Corolla.
equal enough.
This all right. This is our Corolla, right? This is our Corolla, and this is our somebody say it's called a Lambo, right? We should have the higher momentum because
The Lambo, sir, because
Velocity.
he must.
no,
Heavier.
but it has a higher mass, it has a lower mass and a lower velocity.
Lower.
So more.
Oh,
Yeah.
oh,
So
yeah,
this
Corolla.
is faster
No food.
and this weighs more. So this would have a higher momentum, right?
Yes, sir.
Momentum, I fast. How fast
This
is
is
it?
better than this, right?
Yes,
It's
sir.
better. It's a Corolla.
In this case, this will be better than this, right? So the momentum essentially depends on the mass and the velocity. If an object has a higher momentum, a higher mass, and a higher velocity, right,
That's more.
it would have more momentum than this guy over here. That's all we want. We completed, right, our objectives for today. If you have any questions, you can let me know now. If you have any questions, you want me to go over anything in 1 minute?
Our formula again, momentum. I just say
Momentum
formula.
is mass times velocity. Mass
Alright.
times velocity, right?
Yes, sir.
All right. We covered a lot today. These notes will be available on Google Classroom. So you can just check during the day right, to see if it comes up as yet. I'll try to put it up by about 6 o'clock today. I'll try, right?
All right.
You will live.
And I will try and upload the video today also. I see one more message in the chat. All right, good, good, good. Okay, sir. All right, so all the best, everyone.
You know, say only teacher understand, sir.
Thank you so much. I'll take that as a compliment.
Only physics.
We're finished here. If the persons who had questions, you can remain if you want. But if you want, you can go. It's now your lunchtime. You can go ahead. If you have a question, you can stay back and ask me. I think the person was asking me about the distance and displacement. Was asking me about distance and displacement again.
You think I did DeMarco?
DeMarco. Yes. Distance and displacement. You're asking me if it's in the textbook.
Oh no, I tell you, sir.
Oh yeah, sorry.
Oh yeah, maybe I could find like it.
It's not in the textbook. No problem. You won't be required to necessarily write the definition for them. Right? You won't be required to write the definition for them. You just need to know that one is a scalar quantity, one is a vector quantity.
All right.
Yeah, it's not really. You're not required to know the formula or know the definition, right? So which one is it? This one is a scalar quantity again.
Scalar quantity.
Yeah, which one is a scalar? Which one is
scalar? Force and the
distance.
The distance is scalar, and the displacement
is direction and distance where it's going, sir.
The displacement would be vector, right?
Yes, sir.
All right. Any more questions before I end this call? All right.
Sir.
Yeah.
Based on where me there, sir, me now go to something close to internet sometimes.
Okay. All right.
So me not know. Do I have any homework for you, sir?
All right. As it relates to homework, all right. So I'll send a message in the chat. I still need to process this, right? But I gave a homework about a week and a half ago for you to plot a graph, right? Plot a graph. I have graph paper.
Still not get none, sir.
You still not get any?
No, sir. These are rough.
All right. If we're at school, I could just give you graph paper. If I were at school, I could just buy graph paper and give you, right? But you're not going into the town anytime soon?
No, sir.
No. All right.
I think
it's okay.
Make a graph paper.
The aim was that we would actually practice for the lab to draw a graph. So when we come, we'll work on it. All right. When we come, when we actually go back to school for the lab, I'll carry graph paper for you to plot. All right. So you don't have to worry about it. All you need to worry about is the last activity that we did about momentum. Right. So, all right. Okay. I have an idea. I will give you the graph. I plotted a graph already. I will give you the graph, and
yes,
I will post in the group.
Yes, sir.
And you will calculate the gradient and the acceleration due to gravity. Is that better? Is that a better idea?
Yes, sir.
Right. So I give you the graph. I plot the graph already about 2 weeks ago. Right. And we went through it in class. So if you have a problem with it, you can go back to the lecture. Right. You can go back to that one. It's posted on Google Classroom. I think it's about the 21st, October 21st. Right. So I'll give you the graph. I'll send a picture of the graph in the group. And then who is this? You're dead to me. Who is that? Anyway, I'll send it in the group, right? And then you will calculate your gradient and the acceleration due to gravity. I can take that Wednesday. So change of plans, right? I'm trying to accommodate you as best as possible because, as I said, some persons don't have access to the graph leaf. So I'll plot the graph already, and we'll work through that. All right. Any more questions before I end the call?
No, sir.
So,
All right. All right. Good. 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 All the best, guys.
so sir,
Go ahead.
sir, may I ask if you like if me have any outstanding work for you like that only.
That and another one. That and another one with momentum. Right. A simple no, not momentum. All
The
right.
pendulum.
Not the pendulum either. Hooke's law. Hooke's law. So I'll update the activity. Right? Just watch the group. All right? Just watch the group. I'll post everything in the group. So I'll just make it one thing. Question 1, you finish simple pendulum. I'll give you the graph, you calculate the gradient. And then question 2, you do the Hooke's law question. It's just a simple calculation. Like you can do that in 10 minutes. Right? If you follow the notes that I posted.
All right, sir.
All
All
right.
right, sir.
Thanks, guys. All the best.
Yes, sir.
Yes, sir.